just the same thing in reverse. If you create a motor, like some of you already made a motor, if you run that motor in reverse, you can use it to create electricity. And then you've got a generator. And we're going to be going into more precisely how it works as the day goes on. The final notes, this is going to be the last time we're going to do any sort of notes. And it's going to be some stuff I've talked about a little bit, just some odds and ends, things that if I taught you electricity and I didn't go over these things, I'd feel like I did a bad job. And then there's going to be this other part that's going to be really challenging. Some of you are going to get it, and I think you'll probably feel good and it'll be satisfying. But some of you may not get it because it's kind of tricky. If you can visualize things spatially in 3 dimensions, you'll do a little better. If you have trouble with that, this is going to be hard for you. So, those notes that I passed out, get those out if you for some reason put them away. We're just going to go through that, wrap up some things, and then I'm going to have you do a practice quiz to prepare for the quiz that you'll have next class. That'll be the last quiz you'll have. This is the last stuff I'm ever going to teach you formally. And
should I?
So at this point, yeah, just put it on that. Yes?
You have another one.
Another one. Can I give you one that's already been filled out? Is that okay?
Yeah.
It's the practice quiz hasn't been filled out. Oh, you can keep it. I fill out one every class.
Oh my God, it's my new high score even.
I just gotta have a fresh one.
It's not focusing on the screen.
I think is the camera not focusing?
Yeah, it's not focusing.
If you hold this in part way. Let me zoom. Yeah. Okay.
Oh,
Done. Is it out of focus again?
it's like fading.
Okay.
No.
Probably be a better idea to turn the lights off.
Turn the lights off. That should brighten up as time goes by. How's that?
Yeah, that's good.
That's good? Yep. Okay, let me close that up. All right. AC. We went over this with the warm-up last time. Stands for alternating current. And what that means is that the electrons in a wire are just moving back and forth. Yes. My kids have the same pencil, and they keep stealing mine, so I put a label on it. Their initials are scratched into theirs. So that's alternating current. Direct current, DC. And direct current is a continuous stream of electrons traveling from one end of a wire to another. And that circuit construction simulation that you did a while back, there's a version of that has AC and DC. Click on that. And this is showing you AC on the right, DC on the, oh, sorry about that. AC on the right, over here, DC on the left. So batteries are direct current. The electrons just come out one end, go all the way through the circuit, go through the other. So one electron can go all the way through here. With AC, these electrons push those electrons, but no one electron goes from one end to the other.
Is that what a strobe light is?
No. I can change the frequency a little bit. If I change it, I just changed it to 0.5 hertz. So that it goes through half a cycle per second. So every 2 seconds, these are reversing now. In real life, the AC that we have coming out of our walls is 60 hertz. So this back and forth happens 60 times per second. If it were really like this, if it were 2 hertz, then you'd see all the light bulbs go bright, dim, bright, dim, bright, dim every half a second. But because it's so fast, it's 60 times a second, they don't have time for the filament to cool off and then heat up and then cool off and then heat up. It just stays hot, so they work all the time. Some of you might have had experience with fluorescent bulbs, old fluorescent bulbs, where you can see them flickering. That's the AC current switching back and forth 60 times per second. And because they don't have to really heat up and cool off to glow, they can go on and off and on and off and on and off really fast. New bulbs, I don't know what it is about them, but they don't have that problem. Okay, the reason for AC, I went over that last class. It's a two-part thing. The reason that AC is used to deliver power, the reason AC power comes out of the wall is because AC power can be converted from low voltage to high voltage back to low voltage. But that's half the story. The other half is what we want. We want high power lines coming from the next city. We want hundreds of thousands of volts because it's more efficient when power is transmitted at really high voltage. But then we don't want 1,000,000 volts coming out of the wall here. So what we want is power lines to carry really high voltage or really high efficiencies. Then when they get to our houses, we want to drop that voltage from really high to something safe. And AC power, you can do that. You can't do that with DC. You can't take high voltage DC and bring it down to low voltage DC very easily. So in this first space, I'm going to write power transfer is most efficient at high voltage. And the second part of that is it's easy to change the voltage of AC, but not DC. Change AC voltage but not DC voltage. Yeah, sure. I forgot to show you another thing that this can do. This is AC. This is kind of like the transformer that comes into your house. Showed you a picture of one of those last time. This thing right here. So just imagine that this coil of wire, it's coming in from this distribution line and it's coiled around a big metal core. Then I'll take another coil of wire and I'm going to put that around the same metal core. The two coils of wire aren't touching one another. They're just brought near to one another. When I turn this thing on, the light bulb starts to light up. This is what happens in a transformer. Let's say the power line wire comes in and it wraps around here 1,000 times. And then your wires from your house come out to the transformer and they wrap around 1 time. What that would do is it would take 1,000 volts from the power lines and drop it down to 1 volt. Or it would take 10,000 volts at the power lines and drop it down to 10 volts. So the drop in the voltage is proportional to how many coils you have here versus how many coils you have there. So this is just a simple transformer. You couldn't do this. This thing were DC, this wouldn't work. I'm not going to get into exactly why it wouldn't work. But because AC can do that, that's why we use it. Because it allows us to go from high voltage to low voltage. Okay. So we've got the AC and DC stuff out of the way. I told you this would be odds and ends and then Lenz's Law. So these are just kind of random things I wanted to make sure I did at some point. The next part, power. is energy used per second. It's not volts, it's not amps. We haven't talked about it yet. Does anybody know what, can you guess what power is measured in? It's not joules. Joules is overall energy. This is the number of joules of energy used every second. If you have a light bulb, the light bulb will tell you on it how many joules of energy it uses per second. Any guesses what the unit is? Watts. The units are watts. You could also measure power in horsepower. I can't remember exactly how many watts equals 1 horsepower. And the letter for that is W. The formula, this is, if you've got this triangle, it's really 3 formulas. Put power on the top, I right there, and V. Remind me, what's I? What does I stand for? Remember? Current. V is voltage. So power goes on top, voltage, current. I will give you this on a quiz. I don't think this is challenging at all. This is, it's useful, and it'll allow you to answer some problems, but I don't really consider this to be new or earth-shattering or anything, but it will allow you to answer some worthwhile problems. I'm just going to go through these kind of quickly, and you can follow me along. So a light bulb uses 1 amp of current at a household voltage of 120 volts. How much power does it use? I want to calculate power. What would the formula be? Using the triangle up there. What? I times V. Current times voltage. And the current is that the amps or is that the volts? Current, not the volts, it's the amps. 1 amp times 120 volts. And I get 120 what? Watts. So that would be a 120 watt bulb. That's a pretty bright bulb. Number 2, how much current will a 60 watt bulb draw at 120 volts of electric potential? So current is the I. What's the formula for current? P over V. So the power, and the power is watts, 60 watts. I keep doing that. I keep writing 6 watts. 60 watts divided by the voltage of 120 volts. And I get 0.5, what would the units be? Units for current? Amps, or amperes. Number 3 and 4 kind of go together. A table saw draws 15 amps of current, 120 volts. How much power does it use? Power, using the same formula again, is current times voltage, 15 amps times 120 volts equals 1,800, what are the units? Watts. So that's an 1,800 watt table saw. You might, if you're paying the electric company on the electric bill, you probably never looked at one. What are you paying them for? Are you paying them for amps, volts, watts, or something else? They'll say, your power is so many cents. It's 15 cents per what? Is that per volt, per amp, per watt, or something different? Any ideas? But it's actually, you pay them for energy, and their unit that, as far as I know, they still use is kilowatt hours. So this would be 1,800 watts is 1.8 kilowatts. If you left this table saw running for 1 hour, that would be 1.8 kilowatt hours. And that's what you pay. It's so many cents per kilowatt hour. I don't know exactly what my power rate is right now. Now, number 4, if you take the same table saw, this is what I did to my table saw. It was operating on 120 volts. Somebody told me I should switch it to 240 volts, and I was able to do that. So I rewired it so it's now a 240 volt table saw. How much current will it draw? What formula did I use for current? Quick, look at the triangle. P over V. So I know the power of the table saw is what? 1,800 watts. still the same table saw, requiring the same amount of energy per second. And now I've got a different voltage. I've got 240 volts. When I divide that, I get 7.5 amps. So before, it was a 15 amp table saw. Now it's a 7.5 amp table saw. Which one would you guess is going to run cooler? Which one has less of a chance of overheating the
This one.
wires? The 15 amp or the 7.5?
7.5.
7.5. It's got less current going through the wires, so the wires aren't going to heat up as much. So the answer to this question, which of the table saws will run cooler? It's the 7.5 amp saw, because less current causes less heating. And for that reason, I was told that I should, all my shop tools that I was able to convert to 240 volts, I should do that because they last longer. There's less wear and tear on the battery. So we got through 2 sections here. We did AC and DC, and then we did power voltage current. None of this stuff is really that hard. If you study this, do the practice quiz, I think you'll be fine. Now we're going to get to the hard stuff. And there's really only one thing on this page that I'm requiring you to hold on to. There's going to be a bonus question on your quiz based on these, but let's skip to the very back of this packet. The very back. Number 13. Number 13 that's the last question on this practice quiz. You're going to have this question on the actual quiz. It says, explain in simple terms how a generator creates electric current. I think I mentioned earlier that you can call this a generator. In my opinion, this is a generator because I'm taking gravitational energy and I'm creating electrical energy. I'm creating current flowing around and around this copper pipe. This is a generator. So in simple terms, what's happening? I just have a magnetic field moving in relation to a coil. I don't have to have a pipe. I could just have one little coil of wire like that, and I can take a magnet and go and move it closer, move it farther away, turn the magnet around, spin it. In all those cases, I'm going to get current running through the coil. It may not be a lot of current, but it'll be some. So I'm just jumping to this so that when we go over this hard stuff in a minute, you're not going to have to really worry about it because you'll know this is all you really, really have to remember. So how do generators create electric current? A magnet moves relative to a conducting coil. So it could be that you've got a coil that you spin around next to a magnet. It could be that you've got a magnet that you spin around next to a coil. It could be you just don't spin either one, but you move the coil back and forth or the magnet back and forth. In all those cases, you're going to get current, electrical current being created. So now let's go back to this. And this, when we get down to the line right here, this is where things are going to get difficult. But I think that if you really follow along, you're going to be able to do it. So there was a guy named Faraday. He wasn't actually the first person to come up with this. Somebody else came up with it in the United States, but back then people couldn't communicate across the seas really quickly. So nobody knew that this other guy in the United States came up with Faraday's law. Faraday said, a change in the magnetic environment of a coil induces voltage and current. What that means is what I've just been saying. If you move this, you move the magnet down. If I drop this, as the magnet goes down, that's creating the magnetic environment. So where my pencil is right now, as the magnet comes closer, the magnetic field's getting stronger. Now it's getting weaker. So the magnetic environment is changing, and that creates voltage and current going around this thing. Then this guy Lenz, he added to this. He said, not only is that true, but as you drop this through, the current that's created creates its own magnetic field that opposes this motion. So that's why when I drop this down, it goes so slowly, because its movement is creating a current, and that current's creating a new magnetic field, and that new magnetic field is fighting the old one. It's slowing this thing down. So that's kind of the background. I'm never going to ask you about those two guys. I just want to put it on there, because I think it helps to understand. This next part about generators being motors in reverse, this is nothing really new either. I just wanted to state it in maybe clearer terms. An electric current moving through a coil of wire can create a magnetic field. You did that with the solenoids. You had a coil of wire that went around a nail, and when you ran current through there, it became a magnet. This magnetic field can be made to interact with a permanent magnet. So some of you got to that. You made a coil, you ran electricity through it, you held a magnet next to it, and that made a motor. Now, so that's sort of, everything up to there is sort of describing how motors work. A magnetic field moving relative to a coil in a wire can create current. And this concept can be used to create a generator. Motor and generator, they're the opposite. A motor takes in, you give it electricity, and it gives you force and motion. A generator, you give it force and motion, and it creates electricity. What's the time say on there? When we get to 30, we'll have to restart it.
No, you still got 7.5 minutes.
Okay. So this next part, this is to set the stage for the really hard part. Before we do the hard part, I want you to stretch your brains out so you don't pull a muscle. Number 6, draw the magnetic field lines associated with the bar magnet. Could you do that without me doing it? Could you draw the magnetic field lines around this? Remember how they go? Do they go out of the north, or do they go out of the south?
South.
Out of the north. There's no reason why it has to be that way, except that people decided way back when. This is the way it is. So does anybody have a good way to remember that? I don't know. Ah, there we go. Santa leaves from the North Pole. Yeah, thank you. So there's the magnetic field. Santa leaves from the North Pole. But doesn't he go home to the North Pole after it's all over?
No.
Okay, no. He just leaves and never comes back. Runs away from home.
Don't complicate it.
Okay, so number 7, I don't really care if we show this, just again, I want to talk about it. Where in this whole thing, where would the magnetic field be the strongest? Or if I had a little piece of metal, where would I put it so that it would have the strongest pull toward the magnet? I've got it here. Where can I move it so it's going to be pulled with more force toward the magnet? Come on. I'll give you 3 choices. I'll give you 2 choices. No, 3. Here, A, B, or C? B, right there. Okay, I'll give you 3 more choices. A, B, or C? B, right there. So this is where the magnetic field's strongest. Also here. With the little piece of metal, it doesn't have polarity, so it doesn't really matter whether you put it here or here. The pull's probably going to be about the same. And there are 2 ways to explain why that magnetic pull is strong. The most obvious one is the magnetic field stronger far away from the magnet or close to it?
Closer.
Close to it. So that's one thing I'm going to write. The other is, look at these field lines. If I drew a little circle, look at the lines in my circle. If I drew a circle here, look at the lines in my circle. When you've got a stronger magnetic field, they're closer together. So from a picture with magnetic field lines, you can tell where the magnetic field is the strongest by looking at how close the lines are or how close you are to the magnet. If you're right here, the magnetic field's not strong even though you're really close, because those field lines are not sprouting out from there. So sometimes it's probably best to think about where the magnetic field lines are closest. I'm going to write both of those things. Closer to magnet equals stronger. And I'm also going to say stronger when the magnetic field lines are closer together. All right. We're about to get to the really hard part. And I'm going to walk you through this process 2 or 3 times, and hopefully after that, you'll be able to do this on your own. If you can do it, I think you'll be really satisfied. Everything will kind of come together, and you'll understand the big picture about how these things work. If you can't do it, remember that number 13 that I showed you a little while ago. If you just remember that, it says, when you move a magnet relative to a coil, you get a generator, you get current. That's good enough. So we stop that for a second, and then restart it. And